Subscribe to the channel so you don't miss out on any of these videos. Imagine the mysteries of the cosmos where vast, silent celestial bodies follow invisible paths, journeying through the fabric of space. Yet, in this silent ballet, planets do not always stay in their assigned orbits, locked in stable cycles around their parent stars. Some break free, drifting from their original homes in cosmic events known as planetary migrations. This phenomenon, both fascinating and puzzling, has shaped the evolution of entire solar systems. But how can such massive objects as planets move from their birthplace, defying gravitational stability? And what does this tell us about the hidden forces at work in our own solar system and in countless other planetary systems scattered across the universe? The science of planetary migration reveals the delicate and dynamic nature of planetary systems, where immense gravitational interactions can shift planets from their original orbits. These migrations are not random or chaotic but driven by specific forces and interactions, including gravitational forces from gas and dust, the influence of sibling planets, and even the power of stars themselves. Over millions or even billions of years, these forces create migrations that can shape the architecture of planetary systems, impacting everything from planetary orbits to the formation of moons and even the habitability of worlds. In our own solar system, planetary migration has likely played a profound role in shaping the arrangement of planets as we know them today. Evidence suggests that, far from being static, the orbits of planets like Jupiter, Saturn, Uranus, and Neptune may have shifted considerably from where they originally formed. This migration could explain anomalies in our system, such as the distribution of asteroids, the presence of icy bodies in the Kuiper Belt, and even the existence of Earth itself as a life-supporting planet. But perhaps even more intriguing are the planetary migrations witnessed in exoplanet systems, where the diversity of planetary types, orbital arrangements, and unexpected characteristics have challenged our understanding of planetary formation. Observations of hot Jupiters, giant gas planets located alarmingly close to their parent stars, as well as super-Earths that defy traditional models, have reshaped our ideas about what a planetary system can look like. Studying these migrations gives us a glimpse into the sheer diversity of planetary systems and the underlying processes that govern the evolution of worlds across the cosmos. To understand planetary migration, we must first explore the nature of planetary formation itself. Most planetary systems begin as dense clouds of gas and dust surrounding a young star, where particles collide and coalesce, forming larger and larger bodies through a process known as accretion. Over time, as these nascent planets grow, they clear their orbits of debris, establishing a seemingly stable structure. Yet, even in these early stages, gravitational interactions between forming planets, as well as with the remaining gas and dust, create forces that can displace these planets from their birthplaces. This process can unfold in various ways, influenced by the specific characteristics of each system and the presence of nearby celestial bodies. The Grand Tack hypothesis, for example, offers insight into the early days of our solar system and suggests that Jupiter, our solar system's largest planet, may have migrated inward toward the Sun before changing course and moving outward again. This movement could have influenced the formation and placement of other planets in our system, affecting the distribution of materials that ultimately led to the creation of rocky planets like Earth. If not for this migration, our solar system might have been populated solely by gas giants, leaving little room for habitable, terrestrial worlds. Similarly, planetary migration plays a central role in explaining the presence of hot Jupiters around other stars. These gas giants orbit extremely close to their stars, much closer than the gas giants in our own solar system. According to prevailing theories, these planets likely formed farther away from their stars, where gas and dust were plentiful. Over time, gravitational interactions caused them to drift inward, settling into a scorching, close orbit that would have been otherwise impossible for a gas giant to occupy had it formed there initially. The discovery of hot Jupiters was one of the first signs that planetary migration was not only possible but common in other systems, challenging the belief that planets maintain the orbits where they originally formed. Various mechanisms drive planetary migration, depending on the conditions in each planetary system. In younger systems, where there is still an abundance of gas and dust, a phenomenon known as disk-driven migration can occur. In this process, a planet interacts with the surrounding protoplanetary disk, creating waves or wakes in the disk material. These wakes exert a gravitational pull on the planet, causing it to lose angular momentum and migrate toward or away from its star. This type of migration is especially common in the early stages of planetary formation, helping to explain why many young systems exhibit unusual orbital configurations. Another mechanism is planet-planet scattering, which often occurs in systems containing multiple large planets. As planets form and grow, their gravitational interactions become more pronounced, leading to chaotic shifts in orbits. In some cases, these interactions can cause planets to be flung out of the system entirely, while others are pushed into different orbits. This process is believed to have played a role in our own solar system, particularly in the case of the so-called NICE model, which proposes that the migration of Jupiter and Saturn disrupted the orbits of Uranus and Neptune, leading to the current configuration of the outer planets. Planetary migration also sheds light on the curious case of rogue planets, worlds that have been completely ejected from their parent systems. These planets, freed from their stars, drift alone in the vast interstellar space, far from any light or warmth. Rogue planets may have been thrown out due to intense gravitational interactions with other massive planets, especially in systems with closely packed gas giants. The existence of rogue planets raises fascinating questions about planetary migration on a larger scale, suggesting that some planets may not only migrate within their systems, but could also be cast out into the cosmic void, traveling alone through the darkness. In our solar system, migration likely influenced not only the placement of planets, but also the formation of smaller bodies, such as asteroids, comets, and moons. The gravitational dance between migrating planets and surrounding debris can shape asteroid belts, creating regions of stability or instability. In particular, the movement of Jupiter and Saturn is thought to have contributed to the scattering of objects in the early solar system, leading to the formation of the asteroid belt between Mars and Jupiter, as well as the Kuiper belt beyond Neptune. This interaction with smaller bodies continues to affect our system, as the gravitational influence of larger planets can still alter the orbits of comets and asteroids, sending them on collision courses with other planets or into the Sun. One of the intriguing aspects of planetary migration is its potential impact on habitability. The positioning of planets in relation to their stars determines the climate and environmental conditions on their surfaces, influencing the potential for life. When planets migrate, they can move into or out of the so-called habitable zone, the region around a star where conditions might support liquid water, a key ingredient for life. This movement can either enhance or diminish the chances of life developing, as planets may experience drastic changes in temperature and radiation levels. In systems with multiple migrating planets, these changes can be even more pronounced, creating environments where habitability fluctuates over time. In the search for extraterrestrial life, understanding planetary migration is essential. Many exoplanets that we have discovered, including those in the habitable zones of their stars, may have undergone migrations that influence their potential for supporting life. By studying the orbits of these planets, scientists can infer whether they are likely to have stable climates, or if they might experience extreme shifts that could hinder the development of life. Additionally, migration can bring icy bodies from the outer regions of a system closer to the star, where they may release water and organic materials, seeding inner planets with essential ingredients for life. This delivery of icy material through migration has significant implications, particularly in systems with rocky planets that may lack their own volatiles or water sources. When icy bodies are pulled from the outer edges of a planetary system to the inner regions, they can deposit water, carbon compounds, and other life-supporting materials onto young planets. This process, often termed late veneer, may have even contributed to Earth's own oceans, bringing the building blocks of life from the far reaches of our solar system. Furthermore, the effects of planetary migration on habitability extend beyond merely delivering water. The gravitational disturbances caused by migrating planets can also induce tectonic activity and internal heating in rocky planets. For example, as a massive gas giant like Jupiter moves inward or outward, its gravitational influence can tug on the inner planets, causing tidal forces that warm their interiors. This heating could create subsurface oceans or drive volcanic activity, which in turn could support microbial life even on planets located outside the conventional habitable zone. In this way, migration can create environments suitable for life in unexpected places, offering new perspectives on where life might thrive. The study of exoplanetary systems has further highlighted the role of migration in shaping planetary environments. Observations have revealed countless planetary systems that look drastically different from our own, with diverse arrangements and unusual planet types. Systems with hot Jupiters, for instance, demonstrate that migration can drive gas giants into close orbits, where they circle their stars in just a few days. These planets, exposed to intense stellar radiation, develop unusual atmospheric properties, including inflated sizes, high winds, and even rain composed of vaporized metals. The extreme nature of these systems offers insight into the far-reaching consequences of migration on planetary environments and atmospheres. Observations of exoplanets have also revealed super-Earths, planets larger than Earth but smaller than Neptune, which are relatively common in other planetary systems but absent in our own. This could suggest that planetary migration played a role in our solar system's specific configuration, perhaps preventing the formation or long-term survival of super-Earths here. Alternatively, it's possible that any super-Earths that did form were ejected from our system by the gravitational influence of migrating gas giants, clearing the way for smaller rocky planets like Earth and Mars to emerge. This highlights the complexity of migration and how it contributes to the unique architecture of each planetary system. One of the most compelling discoveries related to migration is the existence of resonant planetary orbits, where two or more planets settle into synchronized orbits that reflect a stable, gravitational relationship. For instance, in some systems, planets can establish a resonance where one planet completes exactly 2 orbits for every one orbit of a neighboring planet. These resonant configurations are a result of migration, where the planets' orbits adjust until they find a stable harmonic relationship. Resonant orbits provide stability to planetary systems, reducing the likelihood of collision and helping maintain orbital order even in the face of complex gravitational interactions. Systems like these show that migration doesn't always lead to chaotic outcomes but can, instead, create a form of natural balance. The idea of resonance becomes especially important when considering systems with multiple large planets. In our solar system, for example, the orbits of Jupiter and Saturn play a crucial role in stabilizing the inner planets by establishing a balanced gravitational influence. Without this stability, inner planets like Earth might experience significant shifts in their orbits, potentially jeopardizing conditions necessary for life. This intricate balance shows how migration, by setting planets into resonant orbits, can help maintain long-term stability within planetary systems, making them less susceptible to sudden, destabilizing changes. Theories about planetary migration have also helped explain the curious distribution of materials within planetary systems. For example, in the solar system, scientists have long noted the frost line, a region beyond which temperatures were cold enough for volatile compounds like water, ammonia, and methane to condense into solid ice. Planets that formed beyond this line could incorporate ices into their structures, allowing for the formation of gas giants. Migration theory suggests that as giant planets like Jupiter and Saturn moved, they could have redistributed these icy materials, influencing the growth of other planets. This redistribution process may explain why Earth and other terrestrial planets have relatively limited amounts of water compared to icy bodies farther out. While planetary migration provides answers to many cosmic puzzles, it also introduces new questions. For instance, how common are Earth-like planets and systems with migrating gas giants? Do these migrations inevitably lead to destabilized orbits, or can life-bearing planets coexist alongside migrating giants? As we discover more exoplanetary systems, these questions become ever more pressing, as each new system offers its own unique narrative of migration and evolution. In our search for these answers, astronomers use advanced techniques like radial velocity measurements, transit observations, and direct imaging to detect planets around distant stars and infer their orbital paths. By observing wobbles in starlight or periodic dimming events caused by planetary transits, scientists can determine a planet's distance from its star, its size, and even hints of its atmospheric composition. These observations allow us to piece together the migration histories of planets across diverse systems, helping us identify patterns that might explain the underlying rules of planetary movement. One recent advancement in this field has been the detection of planets in so-called compact multi-planet systems, where several planets orbit their star at very close distances. These systems, with their tightly packed planets, are thought to result from extensive migration, as planets likely formed farther out and then moved inward due to gravitational interactions. These compact systems challenge traditional models of planetary formation, suggesting that migration might be more common and influential than previously thought. As astronomers gather more data, simulations and models of planetary migration become crucial tools for understanding these complex processes. Computer models can simulate millions of years of planetary evolution, allowing scientists to test various scenarios and observe how migration affects the formation and stability of planetary systems. These models have shown that migration often leads to a wide variety of outcomes, from stable multi-planet systems to chaotic dispersals where planets are flung out into space. By refining these models, scientists can better predict the types of systems that are likely to contain stable, life-supporting planets, and those where conditions may be too volatile for life to thrive. The mysteries of planetary migration continue to deepen as we expand our view of the universe. The more we learn about other planetary systems, the clearer it becomes that migration plays a crucial role in shaping not just individual worlds, but entire solar systems. This understanding challenges our preconceptions about planetary formation, forcing us to rethink the stable, unchanging image of planets in fixed orbits. Instead, we're beginning to see planetary systems as dynamic, ever-evolving ecosystems, where the migration of planets can create or destroy worlds, dictate the availability of life-sustaining resources, and forge paths that defy our expectations. One particularly compelling idea is that planetary migration could offer a glimpse into the history of our own solar system. If we can identify patterns of migration in other systems that mirror those in ours, we might be able to reconstruct the early movements of our planets with greater precision. For instance, studying the paths of hot Jupiters or compact multi-planet systems might reveal parallels to the migration of Jupiter and Saturn, shedding light on the formative years of our solar system. By examining these ancient movements, we can gain insights into the conditions that made Earth a habitable world, providing clues about the processes that might give rise to habitable planets elsewhere. Ultimately, the science of planetary migration reminds us that the universe is in a constant state of flux, where even the most massive objects are susceptible to movement and change. This dynamism challenges the notion of a stable cosmos and suggests that planetary systems, like galaxies and stars, have life cycles filled with dramatic transformations. Planetary migration may have been a key factor in the emergence of life on Earth, as well as in the destruction of potential life elsewhere. The fate of planets is not fixed. Instead, it is shaped by the gravitational forces, collisions, and interactions that define our universe. As we continue to explore the mysteries of planetary migration, we're reminded of the intricate balance of forces that govern the cosmos. Each planet, each orbit, and each gravitational pull is part of a larger, interconnected web of influence, where the movement of one body can affect the fate of many others. The study of planetary migration allows us to glimpse the complex choreography of planets and stars, revealing a universe that is as unpredictable as it is awe-inspiring. In this cosmic journey, the science of planetary migration stands as a testament to the ever-evolving nature of space, challenging us to rethink what we know about the origins, trajectories, and ultimate fates of the worlds that orbit distant stars, and perhaps even offering new pathways to understanding our own place among the stars. The exploration of planetary migration is not just about understanding the movement of celestial bodies. It's also about recognizing the fragility and interdependence within planetary systems. The fate of any given planet, whether it thrives with life, becomes a barren wasteland, or is entirely ejected from its system, is shaped by the gravitational forces and dynamics around it. This phenomenon serves as a humbling reminder that planets are not isolated entities but participants in a larger, cosmic interplay where even minor shifts can cascade into profound changes. To deepen our understanding of planetary migration, astronomers rely on increasingly sophisticated instruments and techniques. For example, the Kepler and TESS, Transiting Exoplanet Survey satellite, missions have transformed our knowledge of exoplanetary systems, revealing a staggering diversity of worlds and orbital configurations. These missions, by identifying thousands of exoplanets and measuring their orbits, have provided crucial data that inform migration theories. We now know that many planets exist in orbits very different from the ones we see in our solar system, which supports the idea that planetary migration is a common and influential process in the evolution of planetary systems. Additionally, new tools like the James Webb Space Telescope, JWST, are set to push the boundaries of exoplanet observation even further. JWST's capabilities allow scientists to analyze the atmospheres of distant planets, revealing their chemical compositions and thermal properties. By studying these atmospheres, scientists can gain indirect clues about the past migration of these planets. For instance, the presence of water vapor, methane, or carbon dioxide in certain exoplanet atmospheres might hint at a history of inward migration, suggesting that the planet may have formed farther out where ices are more abundant before moving closer to its star. Beyond exoplanet research, scientists are looking at our solar system with fresh eyes, seeking clues that migration events shaped our own planetary neighborhood. The distribution of small objects, such as asteroids and Kuiper belt objects, offers valuable hints. For example, the peculiar orbits of some objects in the outer solar system suggest they were affected by gravitational forces from the giant planets, possibly during migration events. Studying these smaller bodies helps astronomers reconstruct the early movements of Jupiter and Saturn, as well as the ripple effects of their migration on the rest of the solar system. Moreover, some models propose that Uranus and Neptune might have initially formed closer to the Sun and were later pushed outward by interactions with the other gas giants. This outward migration could explain why Uranus and Neptune reside in the cold outer reaches of our solar system, where conditions are quite different from the regions closer to the Sun. This theory also aligns with the observation that Uranus and Neptune are more ice-rich than Jupiter and Saturn, suggesting they originated in a region with more volatile compounds. These planetary migrations may have left other traces in the solar system. For instance, the Late Heavy Bombardment, LHB, a period around 4 billion years ago marked by intense meteor impacts on the Moon and other inner planets, is thought to have been triggered by the movement of the giant planets. As Jupiter and Saturn migrated, they destabilized the orbits of objects in the asteroid belt and Kuiper belt, sending waves of debris hurtling into the inner solar system. This period of bombardment could have delivered water and other essential compounds to the early Earth, setting the stage for life. Another intriguing concept that has emerged from migration studies is the notion of rogue planets. These are planets that have been ejected from their original systems due to gravitational interactions with other planets. In systems where massive planets migrate inward, they can disrupt the orbits of smaller planets, leading to chaotic interactions that sometimes result in planets being flung out of their systems altogether. These rogue planets may now wander through interstellar space, no longer bound to any star. The discovery of such objects raises questions about the role migration might play in creating these nomadic worlds, and it highlights how migration can dramatically alter the fate of a planet. The idea of rogue planets also leads to speculation about the possibility of planetary exchange between stars. In dense star clusters, where stars are close together, gravitational interactions could allow rogue planets to be captured by neighboring stars, effectively transplanting planets from one system to another. This cosmic exchange of worlds could have profound implications for the study of planetary formation and habitability, suggesting that some planetary systems might contain planets that originated around different stars. Although this remains speculative, the prospect of planets migrating between stars adds yet another layer of complexity to our understanding of migration. Planetary migration theories also intersect with the search for extraterrestrial life. If migration plays a significant role in shaping planetary systems, then the environments where life could potentially arise might be much more varied than previously thought. For instance, gas giants that migrate inward could potentially create stable, warm environments on their moons, transforming them into viable habitats. In fact, some scientists believe that the icy moons of Jupiter and Saturn, such as Europa and Enceladus, may have subsurface oceans warmed by tidal forces caused by their gravitational interactions with their parent planets. These moons could serve as analogues for similar bodies in other planetary systems where gas giant migration has created habitable conditions in unlikely places. As we study planetary migration in greater detail, we're also forced to confront the fragility of conditions necessary for life as we know it. If planetary migration had played out even slightly differently in our solar system, Earth might not have ended up in the habitable zone, or it might have experienced a series of catastrophic collisions that would have prevented life from flourishing. This realization underscores the precariousness of habitable conditions and suggests that life-bearing planets might be rarer than once believed. However, migration could also increase the odds of habitability in some cases. If a planet formed too far from its star to support liquid water, migration might bring it inward to a more temperate zone, where conditions become favorable for life. This duality, the potential of migration to both hinder and enhance habitability, adds a layer of complexity to the search for life beyond Earth. As astronomers explore exoplanetary systems, they're increasingly aware that migration might create unexpected opportunities for life, especially on planets and moons that were previously considered inhospitable. In studying planetary migration, scientists are also examining the broader implications for galaxy formation and evolution. Recent research suggests that migration-like processes might occur not only within planetary systems, but on a larger scale, affecting entire galaxies. For instance, massive black holes at the centers of galaxies exert strong gravitational forces that can influence the orbits of stars and other celestial objects over vast distances. In a sense, galaxies themselves experience a form of migration, as stars and even smaller galaxies are drawn inward or flung outward over cosmic timescales. Understanding these dynamics can offer insights into how galactic structures form and evolve, showing that migration is a phenomenon that operates on multiple scales throughout the universe. As our understanding of planetary migration deepens, we're beginning to see that our solar system's configuration, once thought to be typical, is actually quite unique. The fact that Earth orbits within a stable habitable zone, with a protective gas giant like Jupiter nearby to deflect incoming comets and asteroids, may be a rare arrangement. This awareness has shifted our perspective on the likelihood of Earth-like planets in the universe, emphasizing that planetary systems come in an extraordinary variety of forms, many of which may be inhospitable to life as we know it. In essence, planetary migration has reframed our understanding of what makes a planetary system habitable, stable, and capable of supporting life. Rather than seeing planets as fixed entities in unchanging orbits, we now understand them as participants in a cosmic dance, where migration can dramatically alter their fates and the potential for life. By studying these processes, we gain not only insight into the evolution of planets, but also a deeper appreciation for the delicate conditions that allowed life to arise on Earth. Ultimately, the science of planetary migration is a testament to the ever-changing nature of the universe. The movements of planets, stars, and galaxies reveal a cosmos in constant motion, where gravitational forces shape destinies on scales ranging from individual worlds to entire galactic clusters. As we continue to explore these mysteries, we're reminded of the intricate interplay between stability and chaos that governs our universe, an interplay that has, against all odds, created a world capable of contemplating its own origins among the stars. Planetary migration illuminates not only the processes by which planets move but also how the universe continually reshapes itself. The forces at work during migration give us profound insight into the balance of stability and disruption that governs cosmic structures. In planetary systems, this balance determines whether conditions remain favorable for habitability or veer toward chaos. And this delicate equilibrium between formation and destruction offers clues into the architecture of our solar system and others across the galaxy. To understand the details of planetary migration, we need to examine the types of forces and mechanisms that drive these shifts. migration typically occurs in two primary forms, Type 1 and Type 2. Type 1 migration affects smaller, Earth-sized or lower-mass planets, while Type 2 migration is associated with larger gas giants. Each type plays out differently due to variations in gravitational interactions and the density of surrounding disk material. Type 1 migration involves the movement of low-mass planets within a protoplanetary disk, which is a dense, rotating disk of gas and dust around a young star. As these small planets form, they interact with the gas in this disk, creating pressure waves. These waves exert what's called a torque on the planets, influencing their orbits by pushing them inward or outward depending on the density and composition of the surrounding material. Often, the inward torque is stronger, causing the planet to spiral toward the star. Type 1 migration can be surprisingly rapid. Small planets can move across significant distances in relatively short cosmic time frames, sometimes within thousands of years, which is a blink in astronomical terms. Type 2 migration, on the other hand, involves massive planets like Jupiter and Saturn, which are capable of creating gaps in the protoplanetary disk due to their strong gravitational influence. As these giant planets carve out regions within the disk, they become locked in with the disk's motion, causing them to migrate more gradually over time. This type of migration can lead to inward or outward movement depending on the forces at play. While Type 2 migration is generally slower than Type 1, it still has the potential to move planets over substantial distances, reshaping planetary systems. One of the challenges in studying migration is identifying when and how these processes occurred, especially in systems beyond our own. By observing exoplanetary systems at different stages of development, astronomers can piece together the story of planetary migration across the universe. Systems with so-called hot Jupiters, gas giants that orbit perilously close to their stars, provide one of the clearest signs of inward migration. These planets are unlikely to have formed in such close proximity to their stars, where conditions would prevent the formation of large gaseous envelopes. Instead, they likely formed farther out and migrated inward over time. Observing hot Jupiters reveals not only the reality of migration but also the diverse paths planets can take, challenging previous assumptions about planetary system architecture. The inward migration of hot Jupiters poses intriguing questions about their effects on neighboring planets. As these gas giants move closer to their stars, they exert powerful gravitational forces on any nearby planets, which can result in altered orbits, ejections from the system, or even collisions. These disruptions highlight a potentially chaotic aspect of planetary migration, where the presence of a single massive planet can dramatically reshape an entire system. By studying hot Jupiters and their potential impacts on surrounding planets, scientists gain a clearer picture of how migration affects the overall stability and habitability of planetary systems. In our solar system, the idea of migration has also been explored through models of the early movements of Jupiter, Saturn, Uranus, and Neptune. The Grand Tack hypothesis suggests that Jupiter initially migrated inward before being pulled back outward by the influence of Saturn. According to this model, as Jupiter moved inward, it would have cleared away large amounts of material, effectively shaping the early structure of the inner solar system. If this inward migration had continued unchecked, Jupiter might have ended up much closer to the Sun, possibly disrupting the formation of Earth and the other terrestrial planets. However, as Saturn formed and exerted its own gravitational pull, the two giants created a resonance that reversed Jupiter's path, pushing it outward and sparing the inner solar system. The Grand Tack hypothesis offers a compelling explanation for the observed mass distribution in the solar system, and may even account for the asteroid belt's composition. The inward movement of Jupiter could have stripped away lighter materials, while its outward migration allowed the asteroid belt to retain a mix of rocky and icy objects. This model underscores how migration can influence not just individual planets, but also smaller celestial bodies, leaving a fingerprint on the arrangement of materials within a system. Another theory, known as the Nice model, suggests that the outer planets, Jupiter, Saturn, Uranus, and Neptune, initially formed in a much more compact configuration before spreading out to their current orbits. This model posits that a gravitational instability among the gas giants caused a chaotic rearrangement, with Neptune and Uranus moving outward and scattering material in the Kuiper belt. This process could explain the late heavy bombardment period, as destabilized debris from the Kuiper belt likely collided with the inner planets, including Earth. The NICE model, much like the Grand TAC, illustrates how migration can shape not only planetary orbits but also the broader environment within a planetary system. The implications of planetary migration extend to questions about the conditions for life. Migration events could either disrupt or promote habitability depending on their specifics. For instance, if a migrating gas giant moves inward and forces smaller planets into chaotic orbits, those planets might suffer extreme climate shifts or even collisions. On the other hand, inward migration could also deliver water-rich asteroids and comets to the habitable zone, potentially seeding young planets with the compounds necessary for life. In systems with large gas giants, the phenomenon of shepherding may play a protective role. A massive planet like Jupiter can act as a cosmic shield, deflecting comets and asteroids that might otherwise impact inner planets. Jupiter's gravitational influence has likely diverted countless potential impacts from Earth, contributing to the stability that allowed life to evolve. In this sense, migration can lead to the creation of a stable, life-friendly environment under the right conditions. Systems lacking such protective giants might face higher impact rates, which could hinder the development of complex life. The study of planetary migration also intersects with our understanding of planetary atmospheres. As planets migrate, they encounter varying levels of stellar radiation, which can alter atmospheric composition. A planet that migrates closer to its star, for example, may experience atmospheric erosion, where intense radiation strips away lighter elements, potentially leading to a denser, more compact atmosphere. This process could help explain why some exoplanets have unusually thick or thin atmospheres, and it may also provide insights into the history of atmospheric evolution on planets like Mars and Venus. Another intriguing aspect of planetary migration is the concept of snow lines in protoplanetary disks. The snow line is the distance from a star at which volatile compounds like water, carbon dioxide, and methane freeze into solid ices. Planets that form beyond this line can accumulate icy materials, leading to water-rich bodies that could eventually support life if they migrate inward to warmer regions. Understanding snow lines allows scientists to predict where water-rich exoplanets might form, and how migration might bring them closer to their stars, potentially creating habitable conditions. Migration also raises questions about the potential for habitable super-Earths, rocky planets larger than Earth that orbit in the habitable zone of their stars. Many super-Earths likely formed beyond their system's snow line, accumulating ice and other volatiles. If these planets migrate inward, they might become warm enough to sustain liquid water on their surfaces. The discovery of super-Earths in habitable zones has spurred interest in studying their atmospheres for signs of life, and migration may play a key role in determining their potential habitability. The sheer variety of exoplanetary systems discovered so far reinforces the importance of migration in shaping diverse planetary environments. Systems with multiple gas giants, for example, often exhibit complex interactions that can lead to significant orbital changes over time. The gravitational interplay between these giants can create resonances, or synchronized orbits, which can in turn influence the stability of other planets. These resonances act like cosmic clockwork, imposing a rhythm on planetary orbits that can either stabilize or destabilize a system depending on the precise configurations involved. Through the study of these cosmic mechanics, scientists have begun to decode the intricate dance that governs planetary movements. Migration not only moves planets from one orbit to another but also rearranges entire systems, creating environments that vary from chaotic and inhospitable to remarkably stable. By understanding how migration shapes these systems, we gain insight into the forces that have sculpted our solar system and countless others throughout the galaxy. Planetary migration offers a vivid reminder of the dynamic nature of the cosmos. Planets, far from being static objects, are constantly interacting with one another and with the environments around them. This ongoing movement reflects the universe's inherent fluidity, where stability and change coexist on grand scales. As we continue to explore these mysteries, We unlock new perspectives on the complexity of planetary systems and the delicate balance that allows life to exist. Planetary migration ultimately challenges our perception of solar systems as orderly and unchanging. This process underscores the fluid and often chaotic evolution that shapes planetary systems, from birth to maturity. The universe appears less as a static stage and more as a shifting, adapting environment where planets, moons, and stars are subject to the forces of gravity, radiation, and matter itself. Planetary migration is a profound reminder that everything we know about the cosmos is in a state of flux, much like the ever-changing nature of our own planet. The observational evidence for planetary migration comes from a range of sources, notably exoplanet discoveries and our understanding of gas giant formation and movement. In systems with hot Jupiters, we see some of the clearest signs of planetary migration. These gas giants, orbiting close to their stars, likely began much further out in their systems. Due to interactions with the surrounding gas and their protoplanetary disks, they moved inward. This inward movement seems to be a dominant migration pattern in young planetary systems, suggesting that many hot Jupiters may have disrupted any potential inner planets in the process, leading to dramatically altered planetary lineups. Beyond hot Jupiters, the existence of super-Earths and other unusual planetary configurations in exoplanetary systems suggests migration has taken place across a wide spectrum of planetary types. These worlds, many of which lie closer to their stars than similar-sized planets in our solar system, provide hints about how migration might create configurations that defy initial expectations. Unlike our solar system, with gas giants spread far from the Sun, many exoplanetary systems have tightly packed planets, or compact multiples, where numerous planets orbit in relatively close proximity to their star. This arrangement might imply that planets have shifted closer over time due to inward migration forces, which could include gravitational interactions or disk-driven migration within protoplanetary disks. Our own solar system, though different, shows signs that migration processes influenced its formation. The Grand TAC and NICE models suggest that the giant planets, Jupiter, Saturn, Uranus, and Neptune, may not have remained in the orbits where they initially formed. In the Grand TAC hypothesis, Jupiter is believed to have initially moved inward before being pulled back outward by Saturn's influence. This movement would have had sweeping effects on the inner solar system, clearing away materials and preventing the formation of super-Earths near the Sun. Instead, our inner solar system formed smaller terrestrial planets, like Earth, Venus, and Mars. The NICE model, which explains the outer solar system's configuration, theorizes that Jupiter, Saturn, Uranus, and Neptune were once closer together in a more compact formation. A gravitational interaction between these planets could have triggered their outward spread, causing them to interact with the Kuiper belt and scattering objects throughout the solar system. This scattering is thought to be responsible for the late heavy bombardment, a period when a vast number of asteroids impacted the inner planets, reshaping their surfaces and potentially affecting early conditions on Earth. These movements likely prevented Earth from forming in an environment crowded with other rocky planets, allowing our planet to develop stable, life-friendly conditions over billions of years. Without such migrations, Earth's story, and indeed, humanity's story, might have been drastically different. Planetary migration models provide insight into how migration can affect habitability in other solar systems. The inward movement of gas giants, for example, could disrupt habitable zones, the regions around stars where conditions are just right for liquid water to exist. Gas giants migrating into these zones can destabilize smaller, rocky planets or even eject them from the system altogether. This means that systems with hot Jupiters may be less likely to host habitable planets, as the inward movement of these giants often reshapes the entire system. On the other hand, migration might sometimes create favorable conditions for life. Planets that migrate from cold, outer regions into habitable zones might bring with them volatile compounds like water, carbon dioxide, and methane. These compounds, which freeze into ices in colder regions, could be delivered to inner planets as these worlds move closer to their star. This delivery of key compounds could help seed habitable planets with the elements necessary for life. The influence of migration on habitability brings us to an interesting question. Can life exist on planets that undergo migration? Scientists theorize that migrating planets could retain stable conditions depending on the nature and speed of their movement. Planets that migrate slowly might gradually adapt to changes in radiation, temperature, and atmospheric composition, potentially allowing life to evolve along with these shifts. However, rapid migration or close encounters with large planets could destabilize a migrating planet, causing extreme climate changes or atmosphere loss, thus making life difficult to sustain. One potential example of a migration-affected world in our solar system is Mars. Some scientists speculate that Mars may have migrated slightly inward over time, which could explain its dry, desolate state today. Early in its history, Mars had liquid water on its surface, evidenced by dried-up riverbeds, deltas, and mineral deposits. If Mars indeed moved closer to the Sun over millions of years, this shift might have caused it to lose much of its water and atmosphere, transforming it from a potentially habitable world into the barren planet we see today. Though this remains speculative, Mars's history could suggest that even slight changes in a planet's orbit can have profound consequences for its environment and potential for life. The study of planetary migration also has implications for the search for extraterrestrial intelligence, SETI. If migration is a common occurrence across planetary systems, it may mean that the conditions required for intelligent life are rarer than previously thought. Intelligent civilizations may need not only stable planets, but also planetary arrangements that avoid disruptive migrations. Systems with tightly packed planets, for example, could be prone to gravitational instabilities that increase the likelihood of planetary migration. In such systems, any potentially habitable worlds might experience extreme climatic shifts, reducing the likelihood of long-term habitability required for intelligence to evolve. Conversely, the movement of planets could occasionally create favorable conditions for the emergence of intelligent life by transporting volatile-rich bodies into habitable zones. Migration could serve as a delivery mechanism, providing developing worlds with essential compounds and helping to fertilize them with ingredients for life. However, this scenario requires specific conditions, as an excess of volatile delivery could create dense atmospheres that hinder life, while too little could leave planets dry and inhospitable. As we observe more exoplanets, we find patterns that help us identify potential migration signatures. Systems with closely orbiting planets, or hot Jupiters, are likely migration affected, as these configurations would not naturally form so close to a star. By identifying and studying these systems, scientists can build models that predict how migration has shaped not only planetary orbits but also atmospheres, surface conditions, and overall habitability. Beyond our observational studies, advanced simulations help astronomers test migration theories. These simulations recreate conditions within protoplanetary disks, allowing researchers to observe how gravitational forces, gas pressures, and disk interactions drive planetary movement. Through these models, scientists can refine our understanding of migration mechanics, test the role of different forces, and predict potential outcomes for various planetary configurations. In essence, planetary migration reflects the universe's tendency toward complexity and constant change. Planetary systems are not static. They evolve, adapt, and rearrange themselves in response to a web of interwoven forces. This cosmic dynamism is both destructive and creative, erasing old worlds and forging new environments in which life might someday arise. Each new discovery, from distant hot Jupiters to icy super-Earths, adds another layer to our understanding of migration's role in cosmic evolution. As we advance our observational tools, from the James Webb Space Telescope to next-generation observatories, we will uncover more secrets about planetary migration. These discoveries will deepen our comprehension of the universe's mechanics, shedding light on the forces that drive change on scales beyond human experience. By continuing to explore planetary migration, we will unlock answers to some of the most fundamental questions about our place in the cosmos, the potential for life on other worlds, and the delicate cosmic balance that allows life to thrive. This journey through the science of planetary migration and its implications invites us to consider just how much more there is to learn about the cosmos. As new observational techniques and advanced simulations refine our understanding, the role of planetary migration becomes ever more fascinating. It highlights that the universe is not a calm and settled entity, but rather an intricate tapestry of shifting gravitational fields, colliding bodies, and dynamic orbits, each adding to the grand story of celestial evolution. The detection of exoplanets, especially those with unusual orbits, has revealed migration as a key player in the architecture of planetary systems. For instance, the discovery of exoplanets that orbit in unusual planes or at steep inclinations relative to their star's equator provides strong evidence for migration. Such odd inclinations suggest that these planets were displaced from their original orbits, likely by gravitational interactions or the chaotic influence of other planetary bodies within their system. These interactions can send planets spiraling inward or outward, sometimes forcing them into highly elliptical orbits that challenge the stability of the surrounding system. In some cases, migrating planets can even be ejected from their parent system entirely, becoming rogue planets, worlds that drift through the galaxy without a star to orbit. These orphan planets offer a fascinating counterpoint to our models of planetary migration. Instead of settling into a stable configuration, they have been cast adrift, likely due to violent gravitational interactions that disrupted their original paths. Rogue planets underscore the unpredictable nature of migration, revealing a universe filled not just with organized systems, but with wanderers born from gravitational upheaval. Interestingly, the migration process might also influence the chemical makeup of planets. As planets move through different regions of a protoplanetary disk, they encounter varying compositions of gases, dust, and ice. For instance, planets that form beyond the snow line, the distance from a star at which water ice can remain solid, are likely to accumulate large quantities of ice and other volatile compounds. However, if these planets migrate inward closer to their star, they may lose some of these materials due to increased radiation and heat. This inward migration can strip away water and volatiles, potentially affecting the planet's ability to support life or even altering its atmospheric composition entirely. The reverse process, outward migration, can also alter a planet's chemistry. Planets moving away from their star might accumulate more volatile compounds as they cool, potentially forming thicker atmospheres rich in gases like methane, ammonia, or carbon dioxide. This outward shift could theoretically make these planets more conducive to retaining atmospheres, particularly in systems where planets start out close to their stars before moving outward over time. The variations in atmospheric composition we observe among exoplanets hint at these kinds of migrations, where planets' journeys through different parts of their systems lead to chemical diversity. The effect of planetary migration on moons and other satellites is another intriguing area of study. When a planet migrates, it brings any orbiting moons along for the ride, but this journey can alter the gravitational forces acting on those moons. For example, inward migration could increase tidal heating within a moon, potentially transforming it into a geologically active body with volcanic or tectonic activity. Tidal forces could also trigger the formation of subsurface oceans, particularly in icy moons, which we see in some of the moons around Jupiter and Saturn. This process might create environments that are more conducive to life, suggesting that planetary migration could indirectly foster habitability on moons even if the parent planet itself is inhospitable. Migration's effect on moons also extends to orbital stability. As the host planet shifts positions, the orbits of moons and rings can become destabilized, potentially causing collisions or the reformation of satellite systems. This phenomenon could explain some of the irregular satellite orbits we observe in our solar system, particularly around the outer gas giants. These unusual orbits may be relics of an ancient period when the planets themselves migrated, dragging their moons into new and precarious configurations. One of the most significant breakthroughs in understanding planetary migration has been the discovery of multi-planet systems with intricate orbital resonances. In some exoplanetary systems, planets are locked into synchronized orbits where their gravitational influences maintain a delicate balance. This resonance can serve as a stabilizing force, allowing planets to migrate without being scattered or ejected. The TRAPPIST-1 system, with its 7 Earth-sized planets, is one such example. This tightly packed arrangement could only exist if the planets formed further out and then migrated inward in a synchronized fashion, maintaining orbital resonances that prevented destabilizing interactions. Orbital resonances add yet another layer to our understanding of migration's role in planetary system architecture. Resonances may enable planets to coexist in proximity without destructive interference, suggesting that some degree of migration might be essential for the formation of complex systems. In this way, migration doesn't just create chaos, it also creates order, locking planets into stable patterns that could endure for billions of years. As we delve deeper into the role of migration, we encounter new challenges in simulating these dynamic processes. Migratory paths are influenced by countless variables, from the density and temperature of the protoplanetary disk to the gravitational tugs of nearby stars. Advanced simulations, powered by supercomputers and machine learning algorithms, are essential to unraveling this complexity. By inputting real-world data from observations and adjusting variables like disk density, temperature gradients, and planetary mass, scientists can create models that predict migration pathways with increasing accuracy. One promising area of research involves studying migration in young stellar systems. Observing young stars with disks of gas and dust allows scientists to catch migration in action. In these environments, planets are still forming and moving, providing a real-time laboratory for understanding how these processes unfold. The Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile, for instance, has provided high-resolution images of protoplanetary disks with gaps and rings that may signify the presence of migrating planets. By observing these disks at different stages, astronomers can piece together a timeline of migration and examine how it affects disk evolution and planet formation. Another avenue for studying migration comes from meteorites and ancient planetary surfaces within our own solar system. The isotopic composition of meteorites provides clues about where different bodies originated. If certain materials in meteorites indicate a source in the outer solar system, it could suggest that these objects were displaced inward through migratory forces. Similarly, surface compositions on planets and moons, such as the prevalence of icy or rocky materials, can hint at their migratory histories. By studying these compositions, scientists can reconstruct the migration timelines of celestial bodies, offering a glimpse into our solar system's tumultuous past. Planetary migration not only shapes individual systems, but also hints at broader cosmic patterns. The types of planetary systems we see may be influenced by the prevalence and nature of migration. For instance, spiral galaxies like the Milky Way, with their structured arms, might foster planetary systems with more orderly migration patterns due to their relatively consistent gravitational environments. In contrast, elliptical galaxies, with their chaotic stellar motions, might see more frequent disruptions and potentially higher rates of rogue planets or unstable systems. This correlation could suggest that galaxies themselves have migration profiles, influencing the likelihood of stable, life-supporting systems. In contemplating the full scope of planetary migration, we realize it is a cornerstone of cosmic evolution, bridging the microscopic forces within a protoplanetary disk to the macroscopic architecture of galaxies. It challenges our perception of the universe as a place of orderly orbits, revealing a dynamic cosmos where movement and change are fundamental. Our understanding of planetary migration is still in its infancy. As technology advances, so too will our ability to detect migration, reconstruct ancient planetary histories, and refine our models. The future of space exploration will likely include missions designed to observe young systems, collect data on rogue planets, and analyze the atmospheres of migratory exoplanets. These efforts will deepen our knowledge, gradually transforming planetary migration from a mysterious phenomenon into a fundamental principle of cosmic evolution. The science of planetary migration speaks to the profound interconnectedness of celestial bodies and the forces that bind them. Through gravitational interactions, gas dynamics, and orbital resonances, planets and stars engage in an ongoing dance, shaping one another's paths and destinies. It's a reminder that the cosmos is a vast, interconnected web, where even the smallest shift can ripple outward, affecting worlds light years away. As we continue to unravel the mysteries of planetary migration, We gain not only insight into the mechanics of planetary systems, but also a deeper appreciation for the intricacies of the universe itself. As we move forward with our understanding of planetary migration, we are pushed to explore questions that dive into the very fabric of our universe. Planetary migration is not just about how planets move, but also about what these movements mean for the potential diversity of worlds and the environments they create. Through this lens, planetary migration may hold clues to one of humanity's biggest questions: are we alone? The impact of migration on habitability cannot be understated. Planets migrating inward from the outer regions of a star's habitable zone might sweep through areas where conditions could temporarily support liquid water, which is often seen as a key ingredient for life as we know it. Some scientists hypothesize that such migrations could bring life-essential materials, like water or organic compounds, to inner rocky planets, essentially seeding them with the building blocks of life. In the case of our own Earth, scientists continue to study whether water arrived here through migrating icy bodies from the outer solar system. Comets and water-rich asteroids that likely formed far from the Sun might have migrated inward due to gravitational interactions with giant planets like Jupiter. These celestial bodies could have collided with Earth, bringing water and organic compounds essential for life. This late heavy bombardment period is thought to have played a significant role in Earth's habitability, and planetary migration may have been a driving factor in delivering these life-giving materials. Beyond simply depositing resources, planetary migration also influences the climates and atmospheres of planets. As planets migrate, they experience changes in temperature and atmospheric pressure, which can significantly alter their climate. A planet that begins its life far from its star and migrates inward may undergo dramatic temperature shifts, influencing the stability of its atmosphere and altering its climate in ways that might either support or hinder the development of life. These climate effects may be especially important in studying exoplanets and other solar systems, where migration might drive unexpected changes in surface conditions. Even the development of moons, which can stabilize a planet's axial tilt, is often linked to planetary migration. A stable tilt, like that of Earth, creates regular seasons, which are believed to support biodiversity and evolutionary processes. Migration could therefore indirectly influence the development of moons and, in turn, affect a planet's ability to maintain a stable climate over geological timescales. Earth's axial tilt and its steady seasonal cycle, for instance, play a crucial role in sustaining diverse ecosystems. Thus, the migratory history of a planet could have a cascading effect, shaping its climate, atmospheric dynamics, and potentially, the emergence of life. Some planetary scientists have suggested that planets with extreme migratory histories might host hybrid climates, worlds that have characteristics of both inner and outer planets. For example, a planet that begins near the frost line, where water ice can form, and migrates inward might retain thick clouds and a cooler atmosphere, even after it moves closer to its star. This kind of hybrid climate could create unusual atmospheric layers or even exotic forms of precipitation, such as methane rain, as observed on Saturn's moon Titan. Migration, therefore, may give rise to planetary environments that would otherwise be impossible, expanding the range of possible climates across the cosmos. Migration's impact on planetary composition is equally profound. As planets migrate inward or outward, they encounter zones within their star's protoplanetary disk that are rich in certain elements and compounds. A migrating planet can thus accumulate diverse materials along its journey, affecting its chemical makeup and potentially its geological structure. We see this in gas giants like Jupiter and Saturn, which possess vast amounts of hydrogen and helium, likely due to their formation in the outer solar system before gravitational forces altered their paths. Similarly, terrestrial planets that migrate through regions rich in metals might acquire dense, rocky cores, which could make them more geologically active, contributing to tectonic activity, volcanic eruptions, and magnetic field generation, key components for sustaining atmospheres. In the context of exoplanets, planetary migration raises tantalizing possibilities for planets that might not initially seem habitable. For example, hot Jupiters are massive, gas-rich planets found extremely close to their stars, where they experience intense heat and radiation. Their proximity to their stars suggests they formed much farther out, where gas giants typically accumulate enough material, and later migrated inward. Although these environments seem hostile, migration theorists propose that some of these gas giants might host exomoons, potentially shielded from the extreme heat by the planet's shadow. These moons could orbit within the habitable zone of their parent planet, raising the possibility of stable, life-supporting environments hidden within otherwise hostile systems. In recent years, astronomers have also discovered super-Earths, planets larger than Earth but smaller than Neptune. Some of these super-Earths are located in close proximity to their stars, where it is unlikely they could have formed. This observation suggests that they migrated inward, likely passing through the habitable zone on their journey. The study of these planets offers insights into how migration might influence the development of atmospheres, and perhaps even the potential for life, on large rocky worlds. Scientists are particularly interested in super-Earths because they are more massive than Earth, which could enable them to hold onto thick atmospheres even as they migrate through warmer regions. This could create climates that are far more complex and diverse than those found on smaller, less massive planets. One of the most fascinating aspects of planetary migration is how it challenges our perceptions of system stability. We once imagined that planets form in set orbits and remain there indefinitely, but migration reveals a dynamic picture. Systems can undergo massive changes over time, with planets swapping places, colliding, or even being ejected. This movement reflects a continuous balancing act, where gravitational forces push and pull planets into new configurations. Migration suggests that even systems that seem stable today may have experienced violent rearrangements in the past, or may undergo future changes that could radically alter their architectures. Our ability to study planetary migration will continue to advance as new observational tools are developed. The James Webb Space Telescope, for example, promises to revolutionize our understanding by capturing high-resolution images of protoplanetary disks and young planetary systems. By studying these systems in their infancy, scientists hope to observe migration in real time, watching as young planets interact with their disks and each other. This could provide a direct glimpse into the processes that have long been theorized, confirming or challenging our current models. Furthermore, the next generation of telescopes, including extremely large ground-based observatories, will provide unprecedented detail on exoplanetary atmospheres and surface compositions. These instruments could reveal chemical signatures that indicate a history of migration, such as the presence of volatile compounds that would only exist if a planet had moved through different temperature zones. This observational data, combined with advancements in computer modeling, will enable scientists to reconstruct the migratory paths of planets with greater accuracy. As we continue to explore the science of planetary migration, we deepen our understanding of the complex forces that shape the universe. Migration illustrates the balance between chaos and order, as gravitational interactions push planets across space, sometimes resulting in violent encounters, but also enabling the formation of stable, resonant systems. This duality is a hallmark of cosmic evolution, where creation and destruction are inseparable, and where planets find their place not through static positioning, but through dynamic movement. Planetary migration challenges us to view our universe not as a series of fixed, orderly structures, but as a dynamic environment marked by continuous change. It reveals that our solar system, our planet, and perhaps even our existence, may be the product of countless migratory events, each one a step in a journey spanning billions of years. Migration adds depth to the story of the cosmos, reminding us that the universe is not just a place, but a process, a vast and unfolding drama where worlds are born, reshaped, and reborn through the invisible dance of gravity. The story of planetary migration invites us to think of our place in the universe as far more interconnected than once imagined. Each migratory shift, whether in our solar system or among distant exoplanetary systems, offers a piece of the cosmic puzzle that has led to the formation of diverse worlds. As we probe deeper, we discover how even slight changes in a planet's position or movement can have profound impacts on the characteristics of entire planetary systems, ultimately influencing which planets develop atmospheres, water, and even the potential for life. One remarkable aspect of planetary migration is the sheer unpredictability and variety it introduces into planetary formation. In the Standard Model, a star forms from a collapsing cloud of gas and dust, surrounded by a disk where planets gradually emerge in stable, circular orbits. But migration has demonstrated that this straightforward story is often interrupted by gravitational instabilities, causing planets to move toward their stars, outward to the edge of the disk, or even into orbits that loop in elliptical paths. These very trajectories defy simple categorization, resulting in a vast range of planetary environments. Observations from the Kepler Space Telescope have revealed an astonishing diversity of planetary systems, showing us how migration processes have led to configurations unlike anything in our own solar system. Some systems contain hot Neptunes that orbit extremely close to their stars, others have planets that orbit in tight, closely packed formations, and still others exhibit odd tilts or misaligned orbits. Planetary migration helps explain this diversity, showing that planets can be pushed, pulled, and repositioned by the gravitational forces of nearby bodies, creating outcomes that might have seemed unimaginable just a few decades ago. One of the more extreme cases in our own solar system is that of Uranus and Neptune, two ice giants that scientists believe did not form where we find them today. These planets are thought to have formed closer to the Sun, in the region now occupied by Jupiter and Saturn, before migrating outward to their current positions. This outward migration may have been driven by gravitational interactions with Jupiter and Saturn, which themselves could have shifted due to the effects of the surrounding protoplanetary disk. The fact that two such massive planets could be relocated in this way underscores the immense forces at play in young planetary systems. The outward migration of Uranus and Neptune may also explain the mysterious Kuiper Belt, a region of icy bodies located beyond Neptune, including dwarf planets like Pluto and Eris. Many scientists believe that as Uranus and Neptune migrated outward, they scattered smaller bodies, pushing them into the outer solar system and helping to form the Kuiper Belt. This scattering process likely created a region of icy debris that has since remained relatively undisturbed. Thus, planetary migration not only affects individual planets, but can reshape entire regions of a solar system, creating belts, gaps, and clusters of material that tell the story of their violent origins. Even within the inner solar system, evidence suggests that early migration played a role in shaping planetary positions and compositions. Mars, for instance, is often thought of as a failed planet, a world that may have started forming in the same region as Earth but was prevented from growing larger by the gravitational influence of Jupiter. If Jupiter migrated inward early in the solar system's history, it could have disrupted the material needed for Mars to reach Earth's size, leading to its relatively small mass. This theory implies that planetary migration affected not only the gas giants but also the size, mass, and composition of terrestrial planets like Mars. Furthermore, planetary migration offers a plausible explanation for certain features of our asteroid belt. This belt, located between Mars and Jupiter, contains a mix of rocky and icy bodies, a combination that seems unusual for its location. Migration theories suggest that Jupiter's movement may have pushed icy bodies from farther out in the solar system into the asteroid belt, mixing them with rocky asteroids from the inner solar system. This could account for the diversity of materials found in the asteroid belt today, supporting the idea that migration can even alter the distribution of small bodies. Another fascinating aspect of migration is its potential role in explaining the eccentric, or non-circular, orbits of some exoplanets. Many exoplanets observed to date have highly elliptical orbits, deviating from the nearly circular paths we see in our solar system. This irregularity could be a result of migration events that disrupted the planet's original orbits. For instance, as giant planets migrate inward, they can destabilize the orbits of smaller planets or moons, causing them to move into eccentric paths. In this way, planetary migration might be responsible for the eccentric architecture of certain systems, demonstrating the dynamic forces at play in planet formation. Planetary migration also ties into the study of hot Jupiters, gas giants that orbit extremely close to their stars. These planets likely did not form in their current locations, as temperatures close to a star would prevent gas giants from accumulating their massive atmospheres. Instead, hot Jupiters are thought to have formed farther out, where cooler temperatures allowed gases to condense, and then migrated inward. This inward journey could have been triggered by interactions with the protoplanetary disk or by gravitational encounters with other planets. Hot Jupiters present a striking example of migration's influence, illustrating how planets can travel from distant, cold regions to orbits just a fraction of the distance from their star compared to Earth. Moreover, the discovery of hot Jupiters has raised questions about their impact on the rest of their planetary systems. As these massive planets migrate inward, they might clear out inner regions of debris and smaller bodies, creating empty gaps or holes in the disk. Such migrations could even disrupt the formation of smaller, rocky planets by depriving these regions of the material needed for planet building. Thus, the presence of a hot Jupiter in a system may limit the potential for smaller, Earth-like planets to form in the habitable zone, impacting the system's overall habitability. These insights into planetary migration are giving scientists new ways to interpret the layout and evolution of solar systems. Migration theories allow us to reimagine the early solar system as a place of intense motion, with planets shifting, colliding, and stabilizing into the configuration we observe today. Each discovery of an eccentric orbit, a hot Jupiter, or an ice giant in an unexpected place adds to the body of evidence for migration, reinforcing the idea that our current view of the cosmos is a snapshot in a constantly evolving process. The ongoing study of planetary migration is not just about understanding how planets move, but also about deciphering the origins of planetary diversity and complexity. Every planet, from the scorching hot Jupiters to the icy Kuiper belt objects, bears the mark of migration. This phenomenon connects our solar system to the countless exoplanetary systems scattered across the galaxy, suggesting that migration is a universal force, capable of shaping worlds in ways both familiar and utterly alien. As research progresses, scientists hope to use migration models to predict the characteristics of undiscovered planets, especially those in regions of space that remain difficult to observe. By understanding how migration operates, we may one day be able to reverse engineer the formation history of exoplanetary systems, uncovering clues about planets we cannot yet see. In this way, migration is not just a process of movement, but a gateway to understanding planetary formation, evolution, and the conditions that might allow life to thrive. Ultimately, planetary migration underscores a profound truth about the cosmos, that it is not a static place, but one of constant motion, transformation, and discovery. Each shift in orbit, each gravitational interaction, and each migration event adds to the story of our universe, a story that, through the science of planetary migration, we are only beginning to comprehend. Planetary migration continues to captivate astronomers and planetary scientists because of how it redefines our understanding of solar system evolution. One of the most astonishing revelations is that migration is not a one-time event. Rather, it can occur multiple times over the lifespan of a planetary system, influenced by everything from gas disk dissipation to gravitational interactions with other celestial bodies. An important factor in planetary migration is the presence and behavior of the protoplanetary disk. These disks, composed of gas and dust surrounding young stars, are where planets form and initially establish their orbits. However, these disks are not uniform. They can feature dense regions, gaps, and waves of material that can push planets inward or outward depending on their relative position and mass. Early in a planetary system's life, interactions with the protoplanetary disk often drive Type I and Type II migrations. In Type I migration, smaller, less massive planets feel gravitational tugs from denser areas within the disk. These gravitational forces tend to create asymmetrical pressure zones around the planet, causing it to drift inward. Type I migration is particularly fast and can potentially pull planets closer to their star in just a few 100,000 years, a relatively short time span in astronomical terms. Scientists believe that many rocky, super-Earth-sized exoplanets, especially those discovered close to their host stars, underwent Type I migration early in their formation, moving inward from cooler regions to warmer, inner orbits. Type 2 migration, on the other hand, generally applies to larger, more massive planets, usually gas giants, embedded within the disk. As these massive planets open up gaps in the protoplanetary disk, they essentially create a cleared path around their orbit, moving inward more gradually. This type of migration is often associated with the formation of hot Jupiters, which are gas giants in close orbits around their stars. Unlike Type I migration, Type 2 is a slower process, occurring over millions of years. Still, it demonstrates the immense impact that migration has on planetary placement, as it explains why gas giants, which logically should form in colder, outer regions, can end up in intensely hot, inner orbits. The idea that planetary migration is not random but can be systematically influenced by a planet's size, mass, and disk structure opens up new perspectives on how solar systems stabilize over time. For instance, it's believed that some planets are rescued from certain doom through the dissipative nature of protoplanetary disks. As the disk thins and eventually dissipates over millions of years, the gravitational forces driving migration weaken. Planets nearing the inner edge of the disk might halt their inward journey just in time, preserving a balanced orbit rather than spiraling into the star. Theories about planetary migration have also shed light on some intriguing features of our own solar system, such as the Grand Tack hypothesis. According to this hypothesis, Jupiter, the most massive planet in our system, initially migrated inward toward the Sun. This inward migration could have disrupted the formation of terrestrial planets, potentially causing them to be smaller than they might otherwise have been. However, as Saturn began to form and migrate inward as well, a gravitational resonance was created between Jupiter and Saturn, reversing Jupiter's inward movement and sending both planets outward. This tacking maneuver allowed for the formation of Earth and the other inner planets in a relatively calm environment, while also explaining the distribution of asteroids and other small bodies that occupy the asteroid belt. The Grand Tack hypothesis illustrates how planetary migration can have far-reaching implications, not only for the planets themselves but also for the smaller objects within the system. When giant planets shift positions, they disturb the orbits of asteroids and comets, scattering them across the system. This scattering effect can populate asteroid belts and even seed the outer regions with icy bodies, laying the groundwork for features like the Kuiper belt and the Oort cloud. In a very real sense, planetary migration has written parts of our solar system's architecture, influencing the placement of everything from gas giants to distant comets. Another compelling aspect of planetary migration is its role in the potential habitability of planets. Planetary systems where migration has pushed giant planets inward might disrupt habitable zones, the regions around stars where conditions are right for liquid water to exist on planetary surfaces. When giant planets like hot Jupiters migrate too close to their stars, their immense gravitational influence can either sweep away or alter the orbits of potentially habitable planets, pushing them into inhospitable zones or destabilizing their paths entirely. This has implications for the search for extraterrestrial life. Systems with hot Jupiters are less likely to host stable, Earth-like planets in the habitable zone, making them lower priority targets for finding life. On the other hand, migration can sometimes enhance habitability under certain conditions. For instance, if a gas giant migrates outward after forming, it might actually stabilize the orbits of smaller, potentially habitable planets, providing a gravitational shield against incoming comets or asteroids. Additionally, if a giant planet's movement brings it closer to a rocky planet in a stable orbit, it could enrich that planet's surface with volatile materials, like water and organics, through gravitational interactions or by directing icy comets towards it. In this way, migration can either hinder or assist in the development of conditions favorable to life, depending on the timing, direction, and magnitude of these planetary movements. Beyond our own solar system, scientists are uncovering planetary migration scenarios that are entirely alien to us. For instance, some exoplanetary systems contain so-called super-Earths, which are larger than Earth but smaller than Neptune. In many of these systems, super-Earths are located extremely close to their stars, well within the orbit that Mercury occupies around the Sun. These closed-in orbits likely resulted from migration events that pulled these planets inward. The discovery of super-Earths in tight orbits has fueled interest in studying the potential migration mechanisms unique to these systems and exploring why such configurations are absent in our own solar system. One exciting area of research involves the role of binary stars, systems where two stars orbit each other, in planetary migration. The gravitational interactions in binary star systems can create extremely complex environments for planets. In some cases, the gravitational pull between two stars can either enhance or counteract migration, depending on a planet's position relative to both stars. Some planets in binary systems have orbits that periodically shift, or even flip, as a result of these complex gravitational forces, creating a dance that continually alters their distance from the stars. This form of migration adds another layer of complexity to our understanding, showing that even stars themselves can participate in the migratory patterns of planets. Recent research also suggests that planetary migration might explain the unusual axial tilts, or obliquities, of some planets. Uranus, for example, has an extreme tilt, rotating almost sideways relative to its orbit. This unusual tilt may have resulted from a giant impact during a migration event or from gravitational interactions with other migrating bodies. Similarly, the tilts of other planets, including Earth, could be partly due to the gravitational interactions that occurred during their migratory phases, suggesting that migration has shaped not just where planets orbit, but how they spin and tilt as well. Understanding planetary migration also has implications for planet formation theories more broadly. Migration challenges the idea that planets simply form and stay in stable orbits, revealing that the initial locations of planet formation are only part of the story. Instead, migration shows that planets are dynamic objects, capable of moving vast distances and influencing each other's orbits in ways that add layers of complexity to planetary systems. This dynamism forces us to rethink the traditional models of planet formation and adjust them to account for the role of migration. As our telescopes become more advanced, allowing us to observe planets around other stars with increasing precision, we're likely to uncover even more variations on the theme of planetary migration. Future missions, like the James Webb Space Telescope, will provide unprecedented detail about exoplanetary atmospheres and orbital configurations, offering clues about how migration might have shaped these distant systems. By studying these alien planetary systems, we not only gain insights into their unique histories but also refine our understanding of the universal principles of planetary formation and movement. In the grand scope of cosmic evolution, planetary migration underscores the idea that nothing in the universe is truly fixed. The gravitational push and pull that drive planetary migration remind us of the interconnectedness of all celestial objects, from the smallest asteroid to the most massive gas giant. These forces act over millions or even billions of years, gradually reshaping systems and producing the diverse array of planets we observe across the galaxy. With each new discovery, we are learning that migration is a natural and vital part of planetary development, a cosmic dance that ensures no two planetary systems are ever quite alike. This cosmic dance of planetary migration reflects the remarkable interconnectedness of planetary systems, showing that even seemingly minute gravitational interactions have profound, lasting impacts over immense timescales. When scientists observe exoplanets that don't quite fit our models of how planets should orbit, it often signals that these worlds have likely experienced significant migratory journeys. Such findings help refine our understanding of how planetary systems, including our own, could be shaped and reshaped over their lifetimes. Another key mystery of planetary migration involves the concept of resonant chains. These chains form when multiple planets end up in orbits that synchronize with one another. For example, if one planet takes twice as long to orbit its star as a neighboring planet, they are said to be in a 2:1 resonance. These resonant orbits are common among planets that have undergone migration, as the gravitational interactions during migration can lock planets into these patterns. Resonant chains can offer stability in otherwise chaotic systems, preventing planets from crashing into each other or drifting too far apart. Scientists have observed resonant chains in exoplanetary systems like TRAPPIST-1, where several planets orbit in harmony, likely a result of past migration processes. In addition to resonant chains, planetary migration often leads to other forms of dynamical stability and instability in planetary systems. Sometimes, as planets migrate, they create a domino effect, displacing other planets and setting off a series of orbit-shifting events throughout the system. This effect has been observed in simulations where a single migrating gas giant can destabilize an entire planetary system, causing smaller planets to either migrate as well or, in extreme cases, be ejected entirely. These ejections can lead to the creation of rogue planets, worlds that drift through interstellar space, untethered to any star. Scientists believe that rogue planets are more common than previously thought, and some might even harbor atmospheres and geological activity that could support life in a completely isolated environment. The science of planetary migration also touches upon the phenomenon of planetary alignment, where the gravitational pull of one planet can alter the orbits of others, especially when they are in close proximity or have significant mass. In many cases, large gas giants like Jupiter and Saturn are responsible for such gravitational interactions. The fascinating part is that these interactions can sometimes stabilize a planet's orbit, keeping it in a consistent path around its star despite the complex forces at play. However, when these alignments are disrupted or changed due to the evolution of the system, it can lead to dramatic orbital shifts. This shifting alignment might explain the irregular paths of certain objects in the Kuiper belt or the hypothesized existence of Planet 9, a proposed massive planet lurking in the outer reaches of our solar system, potentially hidden due to its far, eccentric orbit caused by past interactions and migrations. Planetary migration also has profound implications for planetary atmospheres. When planets migrate closer to their host stars, their atmospheres can be exposed to intense stellar radiation. This process, known as atmospheric stripping, can erode layers of the atmosphere, altering the planet's composition and sometimes transforming it into a completely different type of world. For instance, gas giants that migrate inward might lose substantial portions of their gaseous envelopes, potentially leaving behind a dense, rocky core. This transformation could explain some unusual exoplanets that resemble super-Earths, but likely started as gas giants before being stripped down by their host stars' intense heat and radiation. Such atmospheric dynamics further underscore the delicate balance involved in planetary migration. When planets experience mild or moderate migration, they may retain much of their original structure and composition. But more extreme migrations can lead to drastic changes, creating worlds that are fundamentally different from the ones that initially formed. Scientists have observed hot Jupiters with unusual atmospheric conditions, like clouds of vaporized metal and exotic compounds, as a result of their proximity to their stars. These extreme cases illustrate how migration doesn't just affect a planet's position, it reshapes its very nature, potentially creating a whole spectrum of previously unimagined worlds. In addition, the concept of migration opens up intriguing possibilities regarding the origins of life. If Earth or similar planets in other systems underwent migration, it raises the question of whether the conditions for life could have shifted as well. For example, if a habitable planet started further from its star and migrated inward, it might have initially formed in an icy, nutrient-rich region before warming up in a more habitable zone. This migration might provide a window of opportunity for life to take hold by gradually warming an otherwise frozen world. On the other hand, if a planet migrates out of a habitable zone, it could find itself in conditions that no longer support life, potentially leading to extinction events or the cessation of biological processes. In the search for extraterrestrial life, planetary migration thus becomes an essential consideration, as it might explain why some planets that seem to be in habitable zones now may not have always been there. For instance, studying the atmospheres and orbital patterns of exoplanets can reveal clues about their migratory history, offering insight into their potential habitability. Scientists are particularly interested in finding water worlds that could have migrated from outer, icy regions to warmer zones, where liquid water, a critical ingredient for life as we know it, might exist on the surface. Migration can even affect the moons of gas giants, adding another layer of complexity to potential habitability. If a gas giant migrates close to its star, any moons orbiting that giant could also shift closer, experiencing increased tidal heating. This heating might create internal geological activity and even subsurface oceans, as we see in some moons of Jupiter and Saturn, like Europa and Enceladus. These moons, warmed by tidal forces from their host planets, could offer hospitable conditions for life, potentially creating environments that would otherwise be inhospitable if they had not experienced migration-related heating. The science of planetary migration reminds us that planetary systems are rarely static. Each migration event rewrites the system's dynamics, influencing everything from planetary atmospheres to orbital configurations and even the potential for life. The consequences of these shifts are vast, affecting not only individual planets, but the entire architecture of the planetary system. As migration continues over billions of years, planetary systems undergo a constant process of change, gradually evolving in ways that may sometimes seem chaotic but often lead to stable, yet complex, arrangements. Planetary migration has become a cornerstone of modern astronomy, providing insights into the forces that shape the cosmos on scales previously thought to be fixed. Every new discovery, whether it's an unusually tilted gas giant, a super-Earth in a close orbit, or a rogue planet drifting alone, adds another piece to the puzzle, showing that our universe is far more dynamic and fluid than once believed. Our study of planetary migration is far from over. With advances in observational technology, such as next-generation telescopes and space missions, scientists will continue to reveal the hidden histories of distant worlds. As we probe deeper into the origins and journeys of exoplanets, we are bound to uncover migrations far more complex than anything we've observed thus far. These discoveries will expand our understanding of what it means to be a planetary system, challenging our assumptions and perhaps leading us to planets, and even forms of life, that we can scarcely imagine today. As we continue to explore the mysteries of planetary migration, one of the most exciting frontiers involves the intricate relationship between migration and the formation of planetary systems. Early in the life of a star, the surrounding protoplanetary disk, composed of gas and dust, plays a pivotal role in the creation of planets. Migration can begin at this stage, even before fully formed planets exist. Through the process of Type I and Type II migration, protoplanets, smaller planetary bodies that are in the early stages of formation, can begin to drift inward or outward within the disk. The gravitational interactions with the surrounding gas of the disk cause these protoplanets to spiral in or out, depending on their mass and the structure of the disk. Type I migration occurs when small, less massive bodies, such as protoplanets, move within the gas-rich disk. The gas exerts a torque on the planet, causing it to move inward toward the star. This is particularly important during the early stages of a planetary system's formation, as it determines where planets eventually settle. Type II migration happens with more massive bodies, fully formed planets that have gathered a significant amount of material and cleared their orbits. The migration of these giant planets is more complicated and can cause massive shifts in the configuration of the planetary system, as we have seen with the outer planets in our solar system. Both types of migration are critical in explaining the current positions of the planets in our system and help to unravel the larger puzzle of how planetary systems evolve over time. The most intriguing aspect of planetary migration, however, is how it relates to the possibility of planetary system stability. Planetary migration isn't a process that happens in isolation. It often leads to a cascading effect that can destabilize nearby planets and create potential for planetary ejections or collisions. During migration, the gravitational pull from one planet can induce resonance, or even chaos in the orbits of other planets in the system. This process can lead to phenomena like planetary scattering, where planets are thrown into highly eccentric orbits or even ejected from the system entirely. We see evidence of this in our own solar system's past. While it is still debated, some researchers propose that a major event in the solar system's early history could have involved the migration of Jupiter and Saturn. These gas giants may have moved inward toward the Sun, creating a chaotic period in which Uranus and Neptune were forced outward. This hypothesized grand tack scenario could explain the current configuration of the outer planets and the relatively narrow asteroid belt. The idea suggests that Jupiter's migration inward, followed by its reversal and outward movement, would have rearranged the positions of the other planets, including the scattering of objects like asteroids and comets. If true, this would show that planetary migration can have far-reaching effects not just on the planets themselves, but on the smaller bodies populating a system. Beyond our solar system, planetary migration has also provided critical insight into the phenomenon of hot Jupiters, gas giants that orbit extremely close to their host stars. Observations of these planets have revealed that they cannot have formed in their current locations due to the intense heat and radiation they receive. Instead, astronomers believe that these hot Jupiters must have migrated inward from colder, more distant orbits. This migration is likely the result of interactions with the protoplanetary disk, and over time, these gas giants spiraled inward due to the drag of the gas in the disk. One of the most fascinating cases of this migration phenomenon is the detection of systems with multiple hot Jupiters. In such systems, the gas giants may have migrated inward but were also influenced by the gravitational interactions with each other. These interactions can lead to highly eccentric orbits, and sometimes these planets can even pass close enough to each other to cause planetary collisions or close encounters, ultimately reshaping the entire system. The diversity of exoplanets we observe in such systems challenges our existing models of planetary formation, indicating that migration is a key force in shaping the architecture of planetary systems across the galaxy. The study of exoplanetary migration has also opened new doors for understanding the habitability of other worlds. As migration can dramatically alter the structure of a planetary system, it raises the intriguing possibility that planets previously thought to be unsuitable for life might actually be prime candidates for the emergence of life. For example, a planet that starts in the outer, icy regions of a star system and then migrates inward could warm up and enter the habitable zone, where liquid water may exist on its surface. If life arose on such a planet, it could have done so in conditions that are vastly different from the expectations we have for life on Earth, making the search for extraterrestrial life even more complex and exciting. One particular focus in the search for habitable exoplanets is understanding how migration affects a planet's ability to retain or lose its atmosphere. Atmospheric retention is critical for any potential life because a planet's atmosphere provides the necessary protection from stellar radiation, helps regulate temperature, and allows for the presence of liquid water. If a planet migrates too close to its star, its atmosphere may be stripped away by the star's intense radiation, leaving behind a barren, inhospitable surface. Conversely, if a planet migrates away from its star, it may lose the warmth needed to sustain liquid water, thus rendering it too cold to support life. Further complicating this issue is the possibility of atmospheric escape during the early stages of a planet's migration. During migration, gas giants and smaller terrestrial planets may experience a phenomenon called thermal escape, in which the intense heat from their host star causes lighter elements in their atmosphere, like hydrogen and helium, to escape into space. This can cause substantial alterations to a planet's atmospheric composition, potentially rendering it uninhabitable. On the other hand, a planet's migration could potentially bring it into a more stable orbit, allowing it to build a thicker atmosphere over time, making it more suitable for life. Interestingly, the migration process itself could also influence a planet's geological activity. As planets move closer to their stars, they can experience increased tidal forces from their host star and neighboring planets. These tidal forces can induce internal heating within the planet, a process known as tidal heating. Tidal heating is a significant driver of geological activity, and can even lead to the formation of subsurface oceans beneath icy moons, such as Europa and Enceladus. These oceans, warmed by tidal forces, could harbor life, or at the very least create the conditions for life to emerge. It is theorized that some of the moons of gas giants, such as Titan and Europa, could harbor environments that are conducive to life, even though they are far from the Sun. The possibility that planetary migration could play a role in creating these environments is a tantalizing prospect that is still being explored. While migration may seem like a chaotic force, it often works in concert with other forces to stabilize the planetary system over time. For example, the migration of gas giants early in a system's life may help clear out debris, preventing smaller bodies like asteroids and comets from destabilizing the system. In some cases, This type of migration could result in the creation of a clean, orbital configuration, where the inner planets are free of the potential hazards posed by leftover planetary material. The study of planetary migration has profound implications not only for our understanding of our own solar system, but also for the search for habitable exoplanets. As we continue to discover new exoplanets with diverse and unique orbital configurations, the role of migration in shaping these systems becomes increasingly clear. The more we learn about how migration influences the formation, stability, and habitability of planets, the better we can understand the broader processes that shape planetary systems across the universe. The intricacies of planetary migration underscore the dynamic nature of planetary systems, providing a framework for understanding how planets and moons evolve, interact, and potentially harbor life. As we push forward into the era of next-generation telescopes and space exploration, our understanding of planetary migration will only deepen, offering new insights into the mechanisms that drive the formation of planetary systems and the potential for life beyond Earth. As we continue to explore the far-reaching effects of planetary migration, it's essential to highlight one of the most fascinating aspects of this process: how migration not only alters the positions of planets, but can also shape the ultimate fate of a planetary system. In many ways, planetary migration serves as a cosmic architect, designing the configuration of a system by determining which planets remain, which are ejected, and how the remaining bodies interact with one another. This cosmic choreography plays a crucial role in whether a planetary system survives intact over billions of years or whether it becomes chaotic and unstable. One of the most notable examples of this kind of planetary migration-induced chaos can be observed in the process known as planetary scattering. When large planets migrate inward or outward, their gravitational interactions with smaller planets or planetary embryos can send those smaller bodies into highly eccentric orbits, sometimes leading to their ejection from the system entirely. This process is thought to have been responsible for the loss of many potential planets in early solar systems, as well as for the scattering of asteroids and comets into the Kuiper belt or Oort cloud. Planetary scattering is particularly important when we consider how it can lead to the formation of planetary systems that are quite different from our own. For example, in some exoplanetary systems, we observe gas giants and rocky planets that are in close proximity to their stars, unlike our own solar system, where the gas giants reside far from the Sun. This difference is believed to be the result of gravitational interactions during planetary migration that displaced some of the original planets in those systems, pushing them toward the inner parts of the system. These scattered planets can also lead to the creation of more complex systems with a mix of smaller, rocky planets and large gas giants in unusual orbits. In systems like these, planets may experience frequent close encounters, leading to the creation of planetary resonances. These resonances are periodic gravitational interactions between two or more planets that can stabilize their orbits over time, allowing them to maintain regular, predictable positions within their system. These resonances can even act as a protective mechanism, preventing further chaotic interactions and allowing for the continued existence of a stable planetary system. However, not all planetary migration is destabilizing. In some cases, migration can actually lead to the stabilization of a planetary system. For example, when large gas giants such as Jupiter migrate inward, they can clear out debris in their path, reducing the chances of catastrophic collisions between smaller bodies like asteroids or comets. This process could have contributed to the relatively low number of large impacts on Earth and the other inner planets of our solar system. By altering the orbits of smaller bodies and deflecting them away from the inner system, Jupiter's migration may have helped ensure a more peaceful existence for Earth and the other rocky planets. The concept of migration-induced stabilization is especially intriguing when we turn our attention to the distant future of planetary systems. Over the course of billions of years, planets continue to migrate in response to a variety of forces, including interactions with other planets, the dissipation of the gas in the protoplanetary disk, and the gradual loss of angular momentum. In our own solar system, for instance, scientists have speculated that the orbits of the gas giants could continue to evolve over time, potentially leading to further migrations or even a shift in the relative positions of the planets. This slow but steady process of migration could ultimately affect the long-term habitability of Earth and the other inner planets, especially as the Sun continues to evolve and grow brighter in the coming billions of years. Interestingly, this ongoing migration can also affect the position of the habitable zone, the region around a star where conditions are right for liquid water to exist on the surface of a planet. As the Sun ages, it will gradually increase in luminosity, causing the habitable zone to move outward. In the distant future, Earth's position in the solar system may no longer fall within this habitable zone, causing the planet to become too hot to sustain life as we know it. However, if migration were to occur, shifting the orbits of the planets, it might be possible for Earth, or another planet in the system, to be relocated into a more favorable orbit, thus allowing life to continue. Such a future scenario, while speculative, highlights the interconnectedness of all the forces driving planetary migration and the evolution of planetary systems. The role of migration in shaping the long-term habitability of planets is an area of active research and continues to provide new insights into how planetary systems evolve over vast periods of time. As we learn more about the mechanisms of migration and the forces at play, we begin to see that the future of our own planet, and indeed, the future of life in the universe, may be intricately tied to the dance of migration, the ever-changing motion of planets within their solar systems. In the search for habitable exoplanets, understanding the role of migration becomes increasingly important. While we have made great strides in detecting Earth-like exoplanets located in the habitable zones of their stars, we must also consider the possibility that these planets may not have always been in those habitable zones. Migration, whether induced by interactions with other planets, the dissipation of a protoplanetary disk, or changes in the star's luminosity, could have caused these planets to move into their current orbits, thus making them suitable for life. This realization opens up new avenues for exploration, as scientists begin to rethink what makes a planet habitable and how planetary systems evolve over time. One of the most exciting prospects in the study of planetary migration is its potential to help us answer some of the biggest questions about life beyond Earth. If migration played a role in the emergence of life on other planets, it could offer us a new perspective on how life might arise in other parts of the galaxy. We might find that planets capable of supporting life are more common than we previously thought, as migration could lead to the creation of habitable environments in unexpected places. This could be a game-changer in the search for extraterrestrial life, as we would no longer need to limit our search to planets that are perfectly positioned within the habitable zone of their star. Instead, we could look for systems where migration has shaped the conditions for life, offering a much broader range of potential habitable planets. The concept of migration also ties into the larger questions of planetary system formation and evolution. As we study exoplanets and their migration histories, we gain a deeper understanding of the processes that govern the formation of planetary systems. These processes are not just random, they are shaped by the interactions between planets, the protoplanetary disk, and the host star. By studying these interactions, we can build more accurate models of how planetary systems form and evolve, offering us a clearer picture of the universe's rich diversity. As our technology advances, we are becoming more capable of studying these distant planetary systems in detail. Next-generation telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, will allow us to peer into the atmospheres of exoplanets with unprecedented clarity. With these tools, we will be able to learn more about the migration histories of these planets, as well as the potential for life in systems that have undergone migration. These discoveries could open up new frontiers in our search for extraterrestrial life and deepen our understanding of the forces that shape the universe. Planetary migration is one of the most fascinating and complex phenomena in the study of planetary systems. It not only helps to explain the current configuration of our solar system but also offers critical insights into the formation and evolution of planetary systems across the galaxy. Whether it's through the migration of gas giants, or the reshaping of planetary orbits, migration plays a key role in the dynamic evolution of planetary systems. As we continue to explore the mysteries of planetary migration, we move ever closer to understanding the forces that govern the birth, life, and potential death of planetary systems, and perhaps even the emergence of life itself. The ongoing exploration of planetary migration is not just a scientific pursuit. It is a journey that could ultimately answer some of humanity's most profound questions about our place in the universe. As we continue to delve into the intricate and fascinating subject of planetary migration, it's crucial to examine the deeper implications of how migration can shape the future of planetary systems, particularly in terms of their habitability and the potential for life. The concept of planetary migration opens up a whole new world of possibilities, especially when it comes to exoplanets, planets orbiting stars outside our solar system. While we have made great strides in discovering Earth-like exoplanets within their star's habitable zone, the reality may be far more complex than we initially thought. One of the most thought-provoking aspects of planetary migration is its ability to make planets that were once too close or too far from their stars suitable for life. Through the process of migration, planets can potentially be nudged into more stable orbits that place them within the habitable zone, where conditions might allow liquid water to exist, an essential ingredient for life as we understand it. This notion that life could potentially exist in places once thought inhospitable is an exciting prospect for astrobiology and the search for extraterrestrial life. As the study of planetary migration continues to unfold, the likelihood that there are numerous, hidden, habitable planets in the universe increases, pushing us to reconsider how we define the conditions that support life. A particularly captivating example of this is how the migration of gas giants could influence the orbits of rocky planets. When large planets like gas giants, think of Jupiter or Saturn, migrate inward or outward through the protoplanetary disk, they can drastically alter the orbits of smaller, terrestrial planets, shifting them closer to or farther from their host star. In some cases, this process can create the perfect conditions for a planet to become habitable, even if it initially fell outside the habitable zone. The process is not necessarily restricted to early stages of planetary system formation either. As a planetary system evolves, gravitational interactions between its planets can cause them to migrate, often driven by the dissipation of the gas disk that once surrounded the star. This process is akin to how the migration of Jupiter in our solar system may have shaped the positions of the inner planets and prevented early catastrophic collisions. Jupiter's movement likely helped to scatter large bodies of debris, such as asteroids, and as a result, its migration helped keep Earth and other inner planets relatively safe from giant impacts. However, the influence of migration is not always beneficial in terms of habitability. In some systems, migration can destabilize planets, pushing them out of the habitable zone and making conditions unsuitable for life. For example, a planet that originally resided in the habitable zone may be pushed too far inward or outward by the migration of a gas giant, sending it into an orbit where it could experience extreme heat or cold, which could make the environment inhospitable for life. This serves as a reminder that while planetary migration offers a fascinating avenue for the potential of life on exoplanets, it is also a double-edged sword, capable of both creating and destroying the delicate balance needed for life. The dynamics of planetary migration also have profound implications for our understanding of the fate of our solar system. Our Sun, like all stars, is undergoing slow changes as it ages. As it gradually becomes brighter, the habitable zone around it will shift outward, meaning that Earth will eventually move out of this zone. This raises questions about the future habitability of Earth and whether planetary migration, either naturally or artificially, could play a role in prolonging its ability to support life. If Earth's orbit were to shift in response to the gravitational interactions with Jupiter or other bodies, there may be a chance for our planet to remain in a more favorable position for a longer period, even as the Sun evolves. In this context, the science of planetary migration also touches upon a far-reaching question: could we, as humans, one day influence the migration of planets within our own solar system? While this idea might sound far-fetched, it opens up intriguing possibilities for future generations. With advancements in technology and space exploration, it's conceivable that humanity could one day possess the tools to manipulate planetary orbits, perhaps not for the sake of habitability, but for long-term survival or colonization. Such ideas fall squarely in the realm of science fiction for now, but in the distant future, we may discover that we are not merely passive observers of planetary migration, but active participants in the shaping of our solar system. Returning to the present, the evidence of planetary migration in our own solar system and in distant exoplanetary systems continues to be an area of intense research. In our own solar system, the evidence for planetary migration is largely based on computer simulations and theoretical models that seek to explain the current configuration of the planets. These models suggest that Jupiter's inward migration and subsequent outward movement could explain the current positions of the gas giants and the asteroid belt. The idea that a planet like Neptune could have migrated inward and later outward could also help to explain the locations of certain objects in the outer solar system, such as the Kuiper belt and the scattered disk. In exoplanetary systems, the evidence for migration is often inferred from the orbits of planets and their interactions with other bodies. Many exoplanet systems feature planets with eccentric orbits, meaning that they do not follow perfectly circular paths around their stars. This eccentricity can be a sign that the planet has undergone some form of migration in its past. Additionally, the discovery of so-called hot Jupiters, gas giants that orbit very close to their stars, suggests that these planets likely started farther out and migrated inward over time. The study of such systems is crucial because it helps to refine our understanding of how planets evolve and what forces are at play in shaping the architecture of a planetary system. These discoveries have significant implications for the study of planetary formation and the search for habitable planets. The fact that migration can play such a key role in the formation of planetary systems suggests that many of the planets we discover may have had different evolutionary paths than we initially assumed. Some may have been far more hospitable to life in the past, only to be displaced by the migration of nearby planets. Others may have experienced a migration that placed them in an ideal location for life to emerge and thrive. In either case, the study of planetary migration offers profound insights into the history and future of planetary systems, both near and far. As technology continues to improve, particularly with the upcoming launches of more advanced space telescopes like the James Webb Space Telescope, we will be able to observe exoplanets with unprecedented detail. This will allow us to directly study the migration histories of planets, including those that may have been influenced by the gravitational interactions of nearby planets. Such observations will deepen our understanding of the complex interplay of forces that shape planetary systems, and in turn, improve our ability to identify planets that could potentially harbor life. Finally, as we look to the future of space exploration, the study of planetary migration is not just an academic pursuit. It has practical implications for how we may one day expand our presence in the universe. Understanding how planets move, interact, and evolve could be crucial for selecting the best targets for human colonization or for developing strategies to protect Earth from potential threats, such as asteroid impacts or the eventual expansion of the Sun. The science of planetary migration, with its far-reaching implications for the evolution of planetary systems, the potential for extraterrestrial life, and the future of humanity itself, is one of the most exciting frontiers in modern astronomy and space exploration. As we continue to probe the mysteries of how planets move, evolve, and interact, we move closer to unlocking some of the most profound secrets of the cosmos, and perhaps even of our own future in the universe. Planetary migration, with its profound implications, also brings to light an interesting connection between the early stages of a planet's formation and its eventual position within a star's habitable zone. Understanding this process allows us to reconsider the typical assumptions about how planets form and settle into stable orbits. This is not merely an academic curiosity, but a question that touches upon the very possibility of life elsewhere in the universe. The idea that planetary migration could potentially guide the development of life by moving planets into the habitable zone is supported by emerging observations. A particularly captivating example of planetary migration is seen in systems where gas giants like Jupiter or Saturn not only migrate inward but also scatter debris across the system. This debris can either form into new planetary bodies or be ejected from the system entirely. These interactions can shape the evolution of smaller planets and alter the environment of any existing life. In fact, some scientists theorize that the presence of gas giants like Jupiter in our solar system played a crucial role in protecting Earth from catastrophic asteroid impacts during its formative years. Jupiter's strong gravitational field could have steered potentially dangerous objects away from Earth, thus fostering conditions that allowed life to develop and thrive. The migration of such massive planets may have played an even larger role than we currently understand, particularly in the early chaotic stages of our solar system's development. Similarly, the discovery of rogue planets, planets that do not orbit any star, but instead wander through interstellar space, adds another fascinating layer to the concept of planetary migration. Rogue planets are thought to form around stars and migrate outwards, possibly being ejected from their original systems due to gravitational interactions or dynamic instability. Alternatively, these planets may have formed in the dense clouds of gas and dust between stars, only to become gravitationally unbound from any star system. The study of rogue planets challenges our traditional understanding of planetary migration, suggesting that planetary systems may not be as stable as we once believed, and that planets can experience far more dynamic and complex histories than previously thought. Moreover, while the migration of planets like Jupiter may help stabilize other planetary orbits and prevent chaotic collisions, migration can also destabilize planetary systems. For example, if the migration of a gas giant leads to the inward movement of another planet, it may push that planet into an orbit that is not only outside the habitable zone, but that also makes it highly unstable. The gravitational tug of a massive planet, especially in a multi-planet system, can create extreme orbital eccentricities. This results in the planet experiencing temperature fluctuations that could render it unsuitable for life. In extreme cases, this destabilization can lead to a planet being ejected from the system altogether or drawn too close to its host star, where it is incinerated. In such cases, the end of a planet's habitability is a stark reminder of the delicate balance that must exist within a planetary system for life to thrive. The outer planets and gas giants in particular hold a unique responsibility in maintaining that balance. Their migrations can either facilitate or disrupt the delicate conditions required for a planet to remain in the habitable zone. It's a truly remarkable system of cosmic choreography that hinges on the subtle interplay of gravitational forces, material distribution, and time. In addition to the direct impacts of migration on planetary orbits, there are also secondary consequences for the wider star system. For example, the migration of gas giants or other massive planets can influence the distribution of materials in a protoplanetary disk, affecting the way planets form in the first place. In our solar system, this is thought to have played a key role in the formation of the asteroid belt. The gravitational influence of Jupiter is believed to have prevented the planetesimals in that region from coalescing into a full-fledged planet, leaving behind only the scattered debris we now see as the asteroid belt. Planetary migration is also integral to understanding the phenomenon of planetary system architectures that we observe in exoplanetary systems. It is becoming increasingly apparent that many exoplanet systems are vastly different from our own. While our solar system features a clear delineation between rocky inner planets and gas giants in the outer regions, many discovered exoplanet systems display planets in orbits that would be unthinkable in our own system. Planets that should have formed far from their stars are instead found in extremely close orbits. For example, hot Jupiters, massive gas giants in close orbits to their stars, are often considered to be products of planetary migration. These planets likely began their existence farther from their host stars and were later pulled inward, likely by interactions with other planets, or the protoplanetary disk itself. The detection of hot Jupiters in particular has led to a major shift in our understanding of planetary formation and migration. Early models of planetary system formation didn't anticipate the existence of these planets, as they seemed to violate the expected rules of planet migration. But as more exoplanets have been discovered, and with the advancement of more sophisticated simulation tools, it's become clear that planetary migration can account for the extreme orbits of such planets. These discoveries also force us to reconsider the stability of other exoplanetary systems, and how migration might have influenced the emergence of life elsewhere. Understanding planetary migration is not just limited to the science of distant exoplanetary systems. it also sheds light on the fate of our own solar system. As we continue to explore the dynamics of planetary migration within our solar system, scientists are able to gain insight into the future of our planet. Will the Earth's orbit be affected by the movement of Jupiter or Saturn in the distant future? Could our own planet one day be ejected from the solar system altogether, as we see in the case of rogue planets? These questions bring us to the core of the ongoing scientific exploration of planetary migration, its implications for the future of humanity. If migration can shape the orbits and environments of planets, it's conceivable that, in the future, we could manipulate planetary orbits for the purpose of extending habitability or for space colonization. This could include intentionally altering the orbit of Earth or even more distant celestial bodies, though such ventures would require technology far beyond our current capabilities. The potential for planetary migration to alter the future of humanity is both exciting and daunting. While the direct manipulation of planetary orbits remains a distant possibility, the study of migration itself provides valuable insights into the behavior of celestial bodies. As humanity ventures further into the cosmos, understanding these forces could be critical in shaping our destiny. This knowledge not only deepens our understanding of the cosmos but also equips us with the tools to survive and thrive in an ever-changing universe. Planetary migration offers a unique window into the processes that shape the formation and evolution of planetary systems. Whether it's the shifting of orbits that brings a planet into the habitable zone or the chaotic influences that can disrupt a planet's stability, the forces at work are awe-inspiring in their complexity and scale. From the formation of our own solar system to the ongoing discovery of exoplanet systems, planetary migration continues to challenge our understanding of the cosmos and its potential for life. With each discovery, we are not just learning about distant worlds. We are gaining new insights into the fundamental laws that govern the universe. As our tools become more sophisticated, and as our understanding of planetary migration deepens, we can only wonder what further mysteries will be uncovered in this exciting area of space science. Perhaps one day, the very same forces that shape the formation of planets will allow us to manipulate the trajectories of celestial bodies to our advantage, ensuring humanity's place in the stars for millennia to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.